What I'm going to talk to you about is what I call Escience, techniques and technologies for 21st century discovery. And here's the way I think about this. Sensor-driven or data-driven science and engineering is transforming science once again. The way science is done, there's theory, and there's experiment, and there's observation. This is how oceanography is done. And theory and experiment and observation obviously relate to each other very closely. Observations suggest theories, which suggest experiments to validate the theory. This is how science has been driven forward for hundreds and hundreds and hundreds of years. About 30 years ago, science was augmented by another approach, and that was computational science. Now, this is a bit of an exaggeration, but I think of computational science over the past 30 years as having been focused on simulation. That is, let high-speed computers take us to places that we can't go. We can't go to the first few days after the Big Bang. We can't go to the explosion of nuclear devices. We can't go to urban dynamics and social experiments. Right? So simulation allows us to explore those sorts of things that we otherwise can't visit, can't touch and feel. And it has been absolutely essential in transforming a set of fields like astronomy and physics and chemistry over the past 30 years. It's been enormously influential, and it's now really joined theory and experiment and observation as a leg of the scientific stool. What's happened in recent years is another form of computational science has been added. That's Escience. And the Sloan Digital Sky Survey is the canonical example. So the difference is Escience is driven by the data rather than by the cycles. And we'll talk about why this is possible and why this transformation is taking place. But it's a second transformation of science driven by high-speed computing and communication. So Escience is driven by the data more than by the cycles. This is a photo of the Apache Point telescope, which was the telescope used for the Sloan Digital Sky Survey. And this project, over the course of 7 years, collected 80 terabytes of raw image data. What's that? Well, it's a lot of zeros. It's just an enormous volume of data, orders of magnitude more than any science project had ever utilized previously. So this data was made available to the entire astronomical community simultaneously, and at the same time it was made available to individuals, to amateur astronomers, to school children and their teachers. So there's an enormous democratization of science that took place, and it was the first time that large-scale science data was ever put in a commercial relational database system. Previously, the way science is done is you write a flat file, or you stick the data in an Excel spreadsheet. I'll say more about this later. But the idea that you would take the data and the metadata and put it in a commercial relational database system and make it available through the web to everyone was absolutely transformative. Gene sequencers, like the next-gen Illumina sequencer, generate a terabyte a day, but this is not some mammoth machine. This sits on a desktop. There's a lab at the University of Washington that has 25 of these. There's a lab on the East Coast that has 100 of them. You'll hear from Larry Smarr shortly, who deals with this sort of data all the time in his center at the University of California at San Diego, right? So again, a lab of 100 of these is generating far more than a Sloan Digital Sky Survey every day just in one lab from desktop gene sequencing machines. I've done a lot of work, as has Larry Smarr and many others, on the Ocean Observatories initiative. The Ocean Observatories initiative has three components. There's a global observatory, a coastal observatory, and a regional cabled observatory, regional scale nodes. This regional scale nodes are being built off the coast of Washington, Oregon, and British Columbia as part of this National Science Foundation project, the goal of which is to transition oceanography from expeditionary to observatory-based science. It's going to be utterly transforming, streaming data back ranging from chemical and physical and biological sensors to HD television photos of what's going on, right? So again, totally transforming, and as with the Sloan Digital Sky Survey, this data becomes available to citizens and school children at the same time that it becomes available to ocean scientists. The web is a source of data, and point-of-sale terminals are a source of data. Right? So all of these are sources of data, and Escience is driven not just by the data, but by the analysis of the data, and that analysis needs to be automated because there's too much of it to look at. There's too much of it in at least 3 dimensions: the rate at which it arrives, the volume, the amount of it, and the complexity or dimensionality, right? How sophisticated is the data? And all of these have increased rapidly over the past couple of years. They're on the Moore's Law curve. I'll say more about that in a second, right? Escience uses a broad spectrum of technologies from computer science and computer engineering and statistics, sensors and sensor networks, broadband backbone networks, you'll hear more about that in a minute, databases and data mining, several of our panelists will talk about that, visualization, machine learning, cluster computing at enormous scale, right? So these are technologies brought to the world over the past 5 and 10 and 20 years by computer science and computer engineering and statistics that are making this data-intensive science possible, okay? The collection, the storage and management, and the automatic exploration and understanding of this data. The question of how you go from data to knowledge to action is what all of 21st century discovery is about.